Hi, Chris Kuzmal here. We're going to talk about related rate functions, in particular those which involve parameterized functions, which you might not always be able to recognize as parameterized functions when the problem is posed. In the case, nevertheless, let's talk about what the solution is for a related rate problem, where, for example, we have an object which has a position that is a function of time in both its x and y coordinate. And so therefore its position is a x of t, a y of t. That just means the position of object A in the x dimension as a function of time, and the position of A in the y dimension is a function of time. Similarly, B has a position, object B has a position Bx of t, By of t. So now we have the positions of our two objects. Once we have these functions at our disposal, it's relatively easy to find out, for example, what the rate of separation is. What is their rate of closure or separation? We find the distance between the objects. This is just the square root of the sum of the squares of the differences between the components. Now that's a mouthful, but it's just what happens when you're trying to compute the distance between the points represented by the position for object A and the position for object B, which is going to be the square root of A x of t minus bx of t squared plus a y of t minus by of t squared. Okay. Now, we're interested in the derivative of t. Well, this is just a function which we need to apply the chain rule to kind of multiple times. So the square root is going to give us, if we're taking the square root of something overall, that means we're going to slap a 1/2 in front of it and then and raise it to the negative 1/2. Okay, and then in the middle, we're going to have just the contents, ax of t minus bx of t squared plus ay of t minus by of t squared. Okay, but that has to now be multiplied by the word times here. All that has to be multiplied by the derivative of the respective contents, which is just going to be, we have something squared, so it's 2 times the thingy, okay, times the derivative of the contents, which is just going to be ax prime of t minus bx prime of t. And we, again, have the exact same form, 2 times ay of t minus by of t times ay prime of t minus by prime of t. So this gives you a general solution for any two objects moving along as a function of time. What is their rate of closure versus, well, what is the distance between them? And then the derivative of the distance is their rate of closure or separation as a function of time. And all you have to do is substitute in, and that's just algebra, okay? Just algebra, of course. Calculus, in my opinion, is two fundamental things. Setting the problem up well, which this provides us a frame, well, this doesn't provide us a framework exactly for setting up the problem well. This is the calculus. We need to set up the problem so we can plug into this recipe, and then we need to execute on the algebra. So setting up the problem so you can plug it into the calculus and then being able to execute on the algebra is what's really the recipe for success for calculus. So, oh, and of course we'd substitute in t for the answer. And now you're executing on, if once you substitute t in for your answer, that's going to be executing on arithmetic, not even algebra, but critical, okay? So here's an example. A is moving north at 10 miles an hour. B is moving south at 20 miles an hour. What's their rate of separation or closure? And you look at this recipe and say, wait, it doesn't fit. And you're right, it doesn't fit, okay? A is moving north at 10 miles an hour. B is moving south at 20 miles an hour. That gives you an upward pointing arrow indicating A's speed and a downward pointing arrow indicating B's speed. But this doesn't tie A and B's X and Y coordinates down well enough because there's a separation that has to be between them. So you have to note that in the problem. Somewhere in the problem, they're going to indicate the separation. In this, if this is your example, moving up and moving down, that's the X coordinates. But what's going on with the Y coordinates? There's typically is going to be a separation. It's typically going to be constant because usually they're only going to vary one of the dimensions, but they might move to do two, and it's not really that difficult. But even that is not sufficient. Okay, the initial conditions for where they start also could vary, and so that's the second thing that you have to consider. Once you have that set up, then you can have the formula for A and B's X and Y coordinates respectively, and you can plug that into the calculus recipe.